everybody, welcome back to my channel. My name is Cha Cha, and today I'm going to be going over electromagnetism and circuits. I'm not going to be talking about wires as in the right-hand rule, as I believe that deserves a video in its own right. And with that being said, let's dive into one of the most difficult topics in physics, and in my opinion, on the MCAT. So in order to truly understand what we're talking about first, we should probably go over some of the basics. So in the MCAT, what you'll typically encounter is visible light, which goes from 400 nanometers, which 400 nanometers, it kind of has wavelengths like this. They're really short together. It's a high frequency, short wavelength, whereas 800 nanometers, they have long and flowing wavelength. They kind of just go with the flow. And visible light, so you have infrared light and also ultraviolet, right? And infrared, hence the name red, right? So it's greater, wavelengths greater than 800 nanometers. So kind of like that relative, where it's even further apart, whereas ultraviolet, it's even closer together. So higher energy, and we'll go over that in a little bit as to why it's high energy. And infrared has lower energy than visible light. And I want to go over complementary colors. So typically, like what's absorbed, you'll see the complementary color is what you actually see. So in order to remember the complementary colors, just think of the rainbow like Roy G. Biv, right? We all learned about it except for indigo, since indigo would put it as 7 colors instead of the 6. So red, if you absorb a red wavelength, you'll see green. Orange, you'll see blue. Yellow, you'll see B. So Roy, then kind of place the other 3 letters or mnemonics on the bottom. So Roy, and then GBIVs. And then 800 nanometers, right? Since red is the longest wavelength and violet has the shortest wavelength. So now I kind of want to get into the equation that you'll typically see for light and the visible light spectrum. So we have v for velocity, which is often the speed of light, which is a constant of 3 times 10 to the 8th meters per second. And I would highly, highly, highly recommend that you memorize this, as this may not be given to you on the MCAT. And it's just a good rule of thumb to know when you're looking at a problem and you're like, I don't know what the velocity is. Typically, it'll be this. And then we have wavelength, which I have here on my little graph. So the wavelength can either be like the apex or it's between 2 amplitudes. And it's typically measured in nanometers. So 10 to the negative 9th is what a nanometer is. So here you can see I have my energy. So -1, 0, and 1. And wavelength over here, I have between 2 of the peaks. It has to be between 2 of the peaks. It doesn't matter if it's at energy at 1, so the apex over here, high amplitude, or in the troughs, -1. Doesn't make a difference. It just has to be between like two equally spaced distances. And typically you'll have it between, a lot of the times you'll see it with amplitude in the positive energy direction. And then we have frequency. So frequency is how often a complete cycle repeats in a given amount of time. So a complete cycle being the wavelength. So it's typically measured in milliseconds, which I have here in the x-axis. And it is the inverse function of a period, which is 1 over t. And so period is how much time does it take a wave cycle to pass through a point. So it's the inverse of frequency, so it's 1 over f. Those are 2 things that, you'll see a lot on MCAT. And now I kind of want to go over why up here I was talking about why ultraviolet light has a higher energy than infrared light. And same being said, why 400 nanometers, so that violet color, has higher energy than red with its 800 nanometer wavelength. So it all comes back to Planck. and Planck's constant and what he discovered a couple centuries ago. So E is equal to HF. These, I cannot stress how important these two equations will be on the MCAT. So V equals lambda times frequency, and E equals H or Planck's constant times frequency. Um, and then we also have E is equal to Planck's constant times C, or the speed of light slash velocity over lambda. And here I kind of have the proof, so you're just kind of plugging and jugging for frequency. So you're going to replace frequency, solve for frequency using the equation up here, V equals lambda times frequency. Um, so solving for this, having for F, we got C over lambda. So you could just replace that for frequency, and this is what you get. And this is kind of proof. Also, Planck's constant is something that you should probably remember as well. So that's 6.63 times 10 to the negative 34 joules per seconds. Also, a watt. So joules, remember, whenever you're talking about energy, you're typically going to use joules. And then all of that to say, in a very complicated term, just kind of a rule of thumb that you should remember is that the shorter, uh, sorry, the shorter the wavelength or um, the higher the energy, or if you increase lambda, you're going to decrease your overall energy. And these are the equations that prove that. And then over here, I have some visible light spectrum for absorbance, then visible light spectrum for emission. Isn't it beautiful how I drew all this? So, when you have a visible light spectrum for absorbance, what is absorbed, like, is not what you see. What you emit, so what is emitted into the atmosphere or reflected back, that is what you see. So as you can see, they're kind of complete and total opposites of each other. So what is not absorbed is emitted. Okay, kind of changing gears a little bit. Now we're gonna kind of go more into the electromagnetic side of this. So real quick, I kind of want to explain what insulators versus conductors are. So an insulator, I think like keep inside. So it's just gonna, the charges are gonna be kind of congregated or like in a specific area. They're not going to be spread out like a conductor. So it doesn't spread or transmit charge very well. So typically think of like nonmetals. So they have the high ionization energies or high electronegativities as well. So these electrons are tightly bound. So they also can be dielectrics, which we'll go more into in depth about in the capacitance section of this video. Whereas conductors, those are like what's spread out. You'll think of a lot of the times of metals when you want the charge to be equally dispersed throughout your system. So electrons are not close to the nucleus. And why is this? Why are metals so good? It's because they have low ionization energies. Remember, those electrons, they're all spread out. They're kind of like, they have a very large electron cloud. So they aren't typically close to nucleus. Like, that's why they are good conductors. It's kind of like pinball. It goes pew, pew, pew all over the place. Whereas insulators, they are very picky. They have to be close to the nucleus for the atom. And now let's go into Coulomb's law. And oh, also electric field lines too. I should probably do that first. So electric field lines, we have a positive charge and then a negative charge. So when something is positive, right? I always like to think about when you're drawing a dipole, kind of shows a plus, right? Like this is a plus sign. Like if you draw a little arrow here, this looks like plus sign. And then this can be the negative side. So plus, right? It's pointing away from the charge. Whereas negative, it's pointing towards the charge. That's just a rule of thumb that I like to think about it. Hopefully that makes sense. And then over here, I have what a coulomb is equal to. So coulomb, also E, is equal to 1.6 times 10 to the negative 19th coulombs. And this is the same value. So it's a negative. Yeah, it's a negative for an electron, but positive for a proton. So it just really makes a difference. Since remember, protons and electrons, they have the same charge, but they just have different masses, as protons are much, much, much bigger than electrons. Therefore, also protons, they have a smaller acceleration than electrons. Remember, because force is equal to mass times acceleration, which is Newton's second law. Yeah. So now also electric field lines too. The more electric field lines that you see, then the more powerful that charge is. So if you were to only see the ones in blue, then that's like kind of fairly weak compared to like if you see the blue and green electric field lines. That means that that source charge or charge in general is much stronger. Coulomb's law. So K is equal to charge 1 as the absolute value times the absolute value of charge 2 over r squared, which is the distance between the charges. Coulomb's constant will most likely be provided on the MCAT. I wouldn't really waste your time memorizing this, but if you want to, just like, if you're super anxious about trying to memorize everything on the test, which I don't really recommend just because I feel like it's kind of wasting energy. It's 9 times 10 to the ninth newtons times meter squared over coulomb squared. And then over here, I kind of have an example. So I have this charge 1, and then I have charge 2, abbreviated Q1 and Q2, respectively. So as you can see, right, when I'm talking about the electric field lines, look, notice how Q2 has much more electric potential. Sorry, not electric potential. Um, electric field lines than source 1 because it has just like a higher absolute value. So 3 is bigger than 2, right? So, and then R, the distance between the two, is around, let's just say, like, I don't know, like, it's like 10. Like, it doesn't really make a difference. 10 meters, whatsoever, even though it's like really big. But, I don't know, I said square. It's 10 meters. Um, so over here I have 10 to 9 times 10 to the ninth, absolute value of 2, absolute value of -3 over 10 squared. So 6 times 9 times 10 to the ninth over 10 squared is equal to 5.4 times 10 to the 8th. Also, a rule of thumb, right? If you have 10 to the ninth over 10 to the second, this is just a quick refresher for exponent rules. You can just do 10 to the ninth minus 10 to the second equals 10 to the seventh. But because you're doing 6 times 9, that's 54 times 10 to the seventh, or 5.4 times 10 to the eighth. If you just move the decimal place over from the ones place to the tens place. That makes sense, hopefully. Um, yeah, and then there's also electric field due to a point charge. So still using that same K constant, K times the absolute value of Q, uppercase Q is also the abbreviation for a source charge. I don't know why they like Q, but that's just the way it is, over R squared, which is the distance from the point charge is acting upon another charge. Remember, -5, that's a pretty big value for a point charge. So it has a lot of electric field lines pointing inwards, and it's negative, right? So they're pointing inwards, not outwards. And this would be 9 times 10 to the ninth times the absolute value of -5 over 10 squared. Then over here I have R equals 10, right? And Z is just the some charge that we don't really care about. We just care about the electric field lines for the source charge just to see how powerful they are. Okay. Now I'm gonna be going over potential energies. So you'll see a lot of very, very similar equations in this section of this video, but we're going to be using R instead of R squared, which is the only distinction really between the two equations, sets of equations that I'm talking about. And I'll go more into why in a little bit, or just surface level as to why. Electric potential energy. So U is often the symbol that will be used for potential energies, and that is equal to K times Q, the source charge times Q over R. So this is very similar to Coulomb's law, but we are looking at energy between the source charge and the charge it is acting upon, and integrated with respect to distance. So integration, right? That's the main reason as to why it's R, not R squared. And then electric potential, oh yeah, electric potential is V volts. Remember, 1V is equal to joules times coulombs, which is similar to the electric field equation. But the energy per unit of the source charge, um, oh yeah, but sorry, but it's the energy per unit of the source charge. That's what electric potential is. And it's in volts. Now we're gonna kind of be going over equal potential lines too. So each point on the line has the same difference in potential. So if you're gonna look at Q here, some charge here compared to here, they're gonna have the same difference in potential because they are the same distance away from Q, because you could sort of think about it as a circle, right? Like if you're gonna look at one point on a circle versus another point on the same circle, then it's the same, right? Because it has the same radius. No work is done as you move along an equal potential line because you're just going around. It's the same radius, it's the same difference of potential, so nothing is changing. I kind of like to think about this. I know this is like, I don't know why, but like Dante and like his the rings of hell, right? So it's like if someone's in like one ring of hell, did they did a crime equal in proportion to another person that is in the same ring of hell. Yeah. Sorry. That's kind of what I like to think about it. Compared to someone that did a way worse crime, right? This will be a different one. This is on a separate ring of hell, and therefore it is has a greater difference in potential than someone that's in a closer ring of hell. And that's kind of the same thing as what potential lines are saying. Um, Now I kind of want to go over circuits. So, you assume electricity flows in the opposite direction of an electron. I don't know why they never changed this because now they know that you're really kind of tracking the flow of electrons, but they decided, nah, we kind of already have all these rules for tracking like not doing it this way instead. So they we're like, okay, let's just keep it as the flow of positive charge. And that is what a circuit is. So you go from positive to negative. So this is a symbol of a battery. You have the positive, so the longer line is on top, and negative, it's a shorter line. And you see these little squiggly lines, that's a symbol for a resistor. Okay, so over here, yeah, okay, let's do this first. Sorry. Let's go over Ohm's law first. Just because I think it's like pretty important. So you have voltage equals I current over times the resistance. Sorry, excuse me. So current I is the flow of charge between 2 points with different potentials. So I is equal to Q over delta T, which makes sense because you're looking at the charge over a particular charge, the flow of charge over a period of time. And the SI for current is an ampere, which is 1 coulombs per second, whereas resistance is the opposition for flow of charge slash current. So it is sort of like friction in a way, if you think about it. So like as a current flows through a wire, there's going to be some resistance because life isn't perfect. We aren't in a vacuum. There's going to be some transmitted of charge into the atmosphere or into the resistor just because the universe craves disorder. So there's never going to be an ideal world where no energy is lost. And our resistance is equal to P, or rho, which is a constant, times length over A, which is an area. And it is also dependent on temperature, even though that is not included in this equation. But as you increase temperature, you're going to increase resistivity. So at length, the longer the resistor is, electrons travel a greater distance. So there's more ways to go wrong. There's more room of error. There's more, those electrons can transmit more energy into the resistor and get released into the atmosphere instead of flowing along in the wire. And then area, you're increasing the pathways in the resistor, which is why it's on the bottom. So conduction, you're increasing the pathways in the resistor, also known as conduction pathways. So think about it like in a highway, right? So if you have more lanes, more express lanes, there is more room for the cars to flow. There's like less congestion. The cars are all happy. Everyone's happy. So there's more, kind of think of like cars are the current in this scenario. So there's more current that can flow without leading to congestion and kind of road raging and quitting as energy flows into the resistor. That's kind of what I like to think about it. Okay, let's talk about Kirchhoff's two rules. I don't know if I said his name right. I'm sorry. All the German names. Uh, so over here we have at the battery for the positive, we have 20 volts. And then over here we have 0 volts as we go throughout, meandering throughout. And this is an example of Kirchhoff's loop law. So the voltage of the source is equal to the sum of the voltage drops. So overall, there has to be 0 voltage at the negative end of the battery, is essentially what this is saying, is that it's all the voltage has gone through into the resistors at the end of the day. And this is why batteries will die eventually. And then the other is Kirchhoff's junction rule, which is an example of the conservation of charge. So basically, this is saying that the current in is equal to the current out. So in this case, I have current 1, which is flowing into the junction. Current 2 is flowing out of the junction, as is current 3. So current 1 is equal to the sum of current 2 plus current 3, which makes sense because you want to have conservation. Like you're not just losing some energy or charge, I guess, right? Since it's Q over delta T is what current is. You're not just losing it randomly. Like you can't have one way be higher than the other. Then power, which is the last thing I kind of want to talk about. So this is the rate that energy is transferred or transformed. So work over some time, I don't know, delta T change in time. And then you have the change, which is also equivalent to the change in energy over time. So I kind of think about power, oh, excuse me, is like the coils inside of a toaster. Remember we were kind of talking about earlier, like with the resistance, it could be kind of like that road rage in a way. So it's burning red hot once there's like a ton of resistance in a toaster oven, and that is what releases thermal energy, which is a consequence of resistance. In a way, also like if you think about like if you're on an airplane, right? And then you land the plane because you're going like so fast, like kind of think about that as a current, like the current's just going so fast. But as soon as you like kind of meet some resistance, which is the form of like the cement for the air or runway, then you kind of burn through your tires. You're losing, it's what burns red hot. So you're kind of losing some of that energy. It has some resistance, and that's kind of the same way. So it's just like a transformance of the resistance into a different type of energy, which is typically thermal energy. So electrical to thermal is, in the most case, what you'll consider for power in electromagnetism. So in that case, power is equal to current times voltage. And from another person's video that they said, twinkle, twinkle, little star, power is equal to I squared R, which is something that I kind of use to help me remember as well. And I squared R is also equal to V squared over R. And these are just kind of all different iterations of Ohm's law, which is what we talked about up here. Uh, okay. First, I want to talk about resistors, and then I'll go into depth over capacitors. So a resistor in series, there's only one path. So there's only one path for that current to travel. They all take the same highway. So essentially, this is saying that R1 plus R2 plus R3 is equal to R total. And then in parallel, there is a choice for which path. You can either go through this junction over here, or you could go through this junction. Oh my gosh. But at the end of the day, you're still going to have the same voltage drop because you have the same ending and start um, points for, so that means that they're pathway independent, sort of like work in a way. Like you're always going to have this voltage over here at the end of the day. It's still going to be zero. So these two pathways, and it also starts at 10 voltage. So that means that the voltage for these two is equivalent. They have the same voltage drop. And then, so therefore, that means that the total resistance between these two resistors is equal to 1 over R1 plus 1 over R2. Um, yeah, and then in this case, I kind of have, because it's in parallel, I just wanted to provide an example. So let's say that this resistor is R1 is 10, hence the 10 here. And this resistor is 5, R2. So remember that in order to add a fraction, you need to have the same denominator. So obviously, it's much easier to multiply 5 times 2 than to divide 10 by 2 in this case. So it'll be equal to 1 over 10 plus 2 over 10, which is equal to 3/10 or 0.3. So remember your fractions and that your denominators have to be equivalent in order to add. Now, for capacitors, these are kind of what hold charges until it releases. So, in one go, which is also known as a discharge. So, a defibrillator, remember when it's like charging, it's kind of like you're rubbing, or if you're like rubbing your hands together, and you like kind of like static shock someone. That's kind of how I like to think about it as well. Or the clouds when you there's like a lightning strike too. That's kind of how I like to think about capacitors. And then there's different ways that you can think about a capacitor. So over here I have capacitance. So I have my positive charge and my negative charge. These are different capacitance plates. They have to be, there has to be a positive and a negatively charged plate, otherwise this will not work, because otherwise there will not be electric field lines that go from positive to negative. And this is equivalent to charge over B, which is the potential difference between the two charges. And it's also equivalent to the permittivity of free space times area, or area of the plates. Remember, the permittivity of free space, that's just essentially saying that there's like, there's nothing here except for air. Like there's no substance between. Like it's not like it's glass or water or what have you. And then A is for the area of the plates. Obviously, if you have a higher area, then that means that you can have a more accumulation of charge. And then the distance between, right? Like if you have something that's like really far apart, just like magnets, right? Like they're not really gonna like react as much. Like there's not as much attraction, I guess. Just like a long distance relationship. Whereas they're close together, if these plates are close together, then they have a high attraction to each other. Like they're more likely to have to react and have high electric field rates. Um, yeah, and this is kind of what I was talking about. So there's uniform electric field. So electric field is equal to voltage over D. distance between the plates. So it's the direction, remember, as I was saying, electric field lines, they always go, well, not always, but if you have a positive charge, right, like it's positive goes outwards, negative goes towards itself. So electric field lines. And then also, I want to talk about the potential energy for a capacitor. So potential energy is equal to 1/2 times capacitance over, times voltage squared. And if you notice, right, this equation is pretty dang similar to something else we've seen. Going back, throwback, Newton, 1/2 mass times voltage squared. Very, very similar, but instead of mass, you have capacitance, and voltage, it's, sorry, velocity, it's voltage, which both are V's, which can be kind of confusing. So when in doubt, if you don't really know an equation and you're talking about potential energy, chances are it's going to be either the equation for kinetic energy or gravitational potential energy. I also want to talk about dielectrics. So dielectrics is instead of having like this permittivity of free space, so or epsilon naught, you have some material that is between the two capacitors, which sort of acts as an insulator. So whether that be like glass, rubber, water, what have you. And the new value of that capacitor will be C prime, which is equivalent to K, which is some constant, times the original capacitance value, whatever that may be. So it always increases. So K can never be less than 1. So it's acting as an insulator, right? So it's like dispersing charge. It's making it flow more readily. So it'll have more of a discharge. Now I want to talk about capacitors in series. So this is kind of the opposite, as you could see, which is why I drew these two together. So in series for a resistor, it's R1 plus R2 plus R3 equals R total. But in series for a capacitor, it's similar to what is parallel for a resistor. So it's 1 over C1 plus 1 over C2 plus 1 over C3 is equal to C total. And they all share a voltage drop when they are in series, so they can't store as much charge, which makes sense. Whereas in parallel, it is very similar to a resistor in series, as C1 plus C2 equals C total, because each capacitor has the same resistance. They do not share a voltage drop. Then for meters, I have really quickly, I want to talk about it. Ammeter is the current in a live wire. Am, sort of like ampere, which is the SI unit for current, whereas voltmeter is the voltage drop between points in a live wire. So vol sort of for voltage. And then ohmmeter is in a dead wire, typically. And it can be used to calculate resistance using Ohm's equation, which is where kind of got its name. Also, I forgot to mention earlier that the SI for resistance, as you'll often see, is an ohm or a mega. That is kind of all I have wanted to talk about for electromagnetism and circuits. Please let me know if there's anything I'm missing or if I made any egregious errors. Once again, my name is Chacha. Good night. Or whatever you're watching this.